let's record this. So I'm recording now. Forgot to, are we recording? Yes, we are. Okay. So, so sorry, the first little bit will be missing. Maybe I'll add that in. I'll edit it after. Okay. So, decimal number system, which is the one which is natural for us human beings. One of the reasons is probably because we have 10 fingers. But so let's take a look at what this is. Okay, so this is a positional system in the sense that the position of a symbol when we write down a number makes a difference where it lies, right? We know this, okay? So we use 10 different symbols to write down numbers, 10 different symbols, which we call digits. And by the way, if you are coming from the French system, this is also a way of introducing or reviewing, whichever, all the terminology in English. So it also is useful from this point of view. So what are the digits? Well, you know those, of course, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are the only symbols we need to write down our numbers. Okay, so let's just illustrate this. If I write in decimal, if I write 8, 2, 5, 3, what does that mean? Right? So what I'm going to do now is write what we call the expanded notation. In some of the exercises, this term will be used. So the 8 here, of course, is actually worth 1,000, right? So for the positional system, so what is this? This is 8 times 1,000. The 2 here, this is in the position for the 100s, right? And then the 5 is in the position for the 10s, and the 3 is in the position of the 1s, right? And of course, you remember powers. So 1,000 is 10 power 3, right? So that's a more compact way of writing it. 100 is 10 power 2, and 10 is 10 power 1. And what is 1? That's 10 power 0, right? Yes, okay. So this is what we call the expanded notation. Yeah, notation. Let's fix that. Sorry about that. Okay, so this is what basically what this means, right? Of course, there's a certain redundancy here, right? Because I'm actually using the notation to explain the notation, but okay, bear with me. So these, okay, so of course we need the powers of 10, and of course we can write fractions also in the same way and recall the negative powers of 10, right? So let's just take a look at this. So recall negative powers, right? So if I write 10 to the power negative 1, it means 1 over 10, right? And 10 to the power negative 2, that's 1 over 10 power 2, which is 1 over 100. 10 to the power minus 3, 1 over 10 power 3, which is 1 over 1,000, and so on, right? So we have the negative powers like this. And so the positional system can be expanded by just, we keep on going from left to right as follows, right? So we'll have the fractional part that we can add in. So here's another example. So let's say I look at 837.526, right? So this is what we call the integer part of the number. This is what we call the fractional part. Okay, And if I expand this, what does it mean? Well, again, we know the integer part is easy, right? We all know that. So that's 8 times 10 power 2 plus 3 times 10 power 1 plus 7 times 10 power 0. And if you keep on going with the powers of 10, we've got 2, 1, 0. Then we go to negative 1. So it'll be 5 times 10 power negative 1 plus 2 times 10 power negative 2 plus 6 times 10 power negative 3, right? And if we had more decimals, then it would just keep on going. Okay, so that's how it works for base 10. So this is, so the decimal system, right, is base 10. Right, so it's the powers of 10 that we're using for when we get to binary, it'll be base 2. Okay, so we'll get there soon enough. But before that, what I want to do is really go back to grade school and review all the basic arithmetic algorithms, okay? Because we're going to do that in binary, so it's important that we know what we're doing, at least in decimal to start with. Okay, so let's review the basic arithmetic algorithms in decimal, and then we'll move on to binary. Okay, so in principle, this is like known stuff. It's super easy, except that in everyday life, we barely ever do that, right? We do it with a calculator, right? So, but we want to know basically how the machine does it, and the machine does it the way we do it by hand, more or less. Okay, we'll discuss that later. So let's review those basic algorithms, because we'll have to use them to see that we actually understand how all this works. So let's, again, do it in decimal, addition. Okay, so we all know how to add numbers, hopefully. Okay, so there are two main ingredients that you have to keep in mind. You have to align your decimal point. This is important. And of course, there is the notion of carry. It's the carries which are the trickier part, right? Okay, so let's do a very simple example. I'm asked to compute 34.215 plus 513.48. So of course, in everyday life, what do? I just grab a calculator and do it, right? If I'm on a desert island and for some reason I have to add those, I take my finger and do it in the sand, okay? So for whatever reason, you'd have to add these two numbers if you're on a desert island, I don't know. But again, the point is not to make you become experts at adding numbers, is for us to review how the algorithm works, okay? So how does this work? Well, I can do it this way. So 513.48, I want to align the points. 34.215. If you don't like those spaces, you can add a 0 there, right? There's no loss. It's the same thing. And of course, this works right to left because of the carries, right? So let's start on the right. So 0 plus 5 is 5. 8 plus 1 is 9. 4 plus 2 is 6. My decimal point is in the same place. 3 plus 4 is 7. I have no carries here, so this is about the easiest problem we can do. 3 and 1 is 4, and 5. So 547.695. Okay, so that's like super easy. And that's it. Okay. All right, let's modify this so that we get a carry. And also I need to be able to add several numbers at a time because of products, okay? If you remember how we do products, we have to add a whole bunch of numbers at the same time. So let's say I'm asked to add 34.215 plus 513, so these are the same numbers, 0.48 plus 2.1326. Okay. Now, we'll see that in binary, this is a bit different, okay? Adding several numbers together in binary is a bit trickier than in decimal. We'll see why that is true next class. But in decimal, this is doable, no problem, unless you have like a huge number of numbers to add together, and then it's a different story. But so let's take a look at how this goes. Let's copy this, and let's just move down here. Then I'll just keep it like that. Okay, so again, I'm going to align my decimal point. I realize this is not the most exciting math you've ever seen. Bear with me. Just enjoy the fact that it's super easy. Hopefully it is. 2.1326. So maybe you want to add zeros here just to keep track. Okay, and then again, of course, it's right to left. So 0, 0, and 6 is 6. 5, 0, and 2 is 7. 8 and 1 is 9, and 3 is 12. So now we have a carry, right? So there's a 2, and I have a carry of 1. And so now 4 and 2 and 1 and 1, that's 8. My decimal point is there. 4, 3, and 2 is 9. 3 and 1 is 4, and 5. So this is my sum, 549.8276, okay? And that's basically how a machine would do it, except it does it in binary. Okay, so here we go. So that's all good, hopefully, for the sum. Oh, sorry. Yes, I will post the notes right after class. Everything that I'm writing down will be available right after class. Okay. Okay. So that's addition. Let's move on to subtraction. Okay. So key ingredients, just like addition, you have to align your decimal points. That's important. And it's not carries now, it's borrows. It works the other way around. And let's be very careful with that as we go, okay? So here is an example. Let's compute 45.217 minus 23.64. Okay, so how do I do that? Okay, so 45.217 minus 23.64. You can put a 0 there if you wish, if it's easier. And again, of course, it's right to left, right? Okay, so let's see. So I start with this digit here. I've got 7 minus 0. This is 7, nice and easy. Then I move on. 1 minus 4, I'm in trouble, right? 1 is smaller than 4, so I need to borrow. So I'm going to borrow 1 of these guys here, so that will leave me only 1. And I bring it over here, right? Which is 10 times more, right? So when I'm moving right, the value, as I'm moving right to left, the value is 10 times as big. So when I'm borrowing here, what I'm getting here is 11, right? So 11 minus 4 is 7. Now I have to subtract 1 minus 6. Again, I need to borrow. So I'm going to take 1 out here. That leaves 4. That's 10 more in this column. So that's 11 minus 6 is 5. My decimal point is right there. 4 minus 3 is 1. I'm happy. 4 minus 2 is 2. So that should be 21.577. Okay. So again, I've just illustrated those borrows. I have no idea how this is. I mean, you've all done this at some point. When's the last time you did it? I don't know. Okay. But in principle, we've all learned this before. So, okay. Do I need to do another example? Maybe I should. Let's try another one. Let's see. Okay, let's do 123.45 minus 75.168. What is that? So again, I'm going to align my decimal points. 75.168. It's this. I'll put a 0 here, right? So I start on the right, 0 minus 8. I need to borrow. That leaves me 4 of those. I had 5, leaves me 4. I've got 10 now more here, so that's 10 minus 8, which is 2. 4 minus 6, I need to borrow. That's 3. 10 more over here, so that's 14 minus 6, which is 8. 3 minus 1 is 2, I'm happy. 3 minus 5, I have to borrow again. I borrow 1 here, so I've got 1 left. 10 more here, so that 13 minus 8, sorry, 13 minus 5 is 8. 1 minus 7, well, okay, so it's 11 minus 7. I'll just do it directly, or you can do the borrow if you prefer. Okay, so this is the result. Hopefully, this is good for everybody. Okay, so we've got, so far so good? Yeah, I guess so. Okay, so we've got plus, minus, you can guess next, multiplication, that's the next guy. So what is that? Multiplication, product. So the basic algorithm is essentially, it's a whole bunch of additions. It's like repeated additions, right? To some extent. But there are some tricky things we have to discuss. So the decimal point here, then it's not a question of aligning at all. It has nothing to do with it because we're multiplying. It goes as follows, and I'll explain in more detail once I've done the example. But in principle, you might remember this, is that if you want to multiply two numbers, when you're doing it, you don't care about the decimal point, right? But if you want to know the position of the decimal point in the result, then you look at your two factors. Okay, so the number of decimals or decimal places in the fractional part of the result is equal to the sum of the number of decimal places in the factors. Okay, I'll illustrate this with an example and you'll see, I'm sure this will ring a bell. Okay, so let's do an example in full. Oops, not that. There we go. So 2.35 times 43.162. I want to multiply this. Okay. Again, when I'm actually doing the product, the decimal points are irrelevant. Okay. I'm just going to remove them from my computation and just use that at the very end only. Okay. So here we go. So I've got wait, I need more room than that. So 43162 times 235. Okay. So again, you see the decimal point, I don't care. And again, I'm going to start on the right and move left. So I start with this guy here. Okay. So what do? I multiply the digits one after another. There will be carries, okay? So 5 times 2 is 10. So that's a 0 here and a carry of 1, okay? Then 5 times 6 is 30 plus 1, that's 31, and that's a carry of 3. 5 times 1 is 5, plus 3 is 8. 5 times 3 is 15, so I have a carry of 1. 4 times 5 is 20, plus 1 is 21. So that's my first multiplication. Basically what I've done is I've multiplied the units digit of 235 times that big number 43162, okay? Next step, you might remember this. So now I'm going to use the next digit, which is 3, okay? This one is not worth 3 though, it's worth 3 times 10. Position is the next in line, right? So the resulting number is worth 10 times more. So you put a 0 there, right? And you repeat exactly the same procedure. So 3 times 2 is 6. 3 times 6 is 18. I have a carry of 1. 3 times 1 is 3 plus 1 is 4. 3 times 3 is 9. 3 times 4 is 12. So this is what I get. If you see me do a mistake, just let me know, okay? My window is, I can't see everything like super well, but I can see the chat. If you raise your hand, I suppose that I'll see it. And if you just open up your mic, if you have a question, don't hesitate. Okay, so I've done the 3 now. So I'm moving on to the 2 here, which is worth 100 more. So I'm going to add 2 zeros here, and I repeat. Okay, so 2 times 2 is 4. 2 times 6 is 12. I'm keeping my carries there. It's getting a bit messy, but 2 times 6 is 12. I've got 1. 2 times 1 and 1, that's 3. 2 times 3 is 6. 2 times 4 is 8. And I hope I didn't mess up. And I think that looks okay. Okay, so I'm done with the multiplying. What's left is you add all these numbers, right? And so here we go. 0, 7, 16, that's 20, carry of 2. That's 13. I have to do it in French in my head. So there's one thing that so French is my first language, and if I do this stuff, I have to do it in French in my head. That's 14. That's 11. And that's 10. And I hope I didn't mess up. That looks okay. All right. So now, very last step, decimal point. Okay. So what do? You look at your factors, and you see that you have 2 decimal places plus 3 decimals. That's a total of 5 decimal places. Okay, so what do? You go here, 1, 2, 3, 4, 5. This is where your decimal point is. Okay, now you can always check this pretty quickly just by looking at the numbers you have. This is 2. This is 43. 2 times 43 is 86, more or less. It's not 800. It's not 8,000. It's not 8. It's 86. Look at the result here, 101 point something. That's in the right size, right? You're not supposed to get 1,000 or 10, so you know you're right. Okay, so the resulting value is 101.4307. You don't need the last 0, obviously, in the decimal place. Hopefully that rings a bell. Might be far, I don't know. Is that good? Is that okay? All right, so we've got plus, minus, multiplication. Plus and minus will be, okay, plus in binary is just the same. It's basically the same, except if you're adding a whole bunch of numbers, it'll be different, a little bit different. Subtraction is essentially the same, and there's a different technique which is super cool that I'll show you next class. Multiplication will be different because you see that we have to add a whole bunch of numbers once we're done with the multiplication, right? So it's going to be just a little bit different when we're doing it in binary, but not much. The next and last operation that we want to review is division. Okay, so that's the last one, and everybody's going like, oh no, not division, right? It's like, ugh. Fortunately, we're not going to divide in binary, okay? I won't have you dividing in binary. We won't do it. In binary, or we're going to do octal also in hex. We're just going to do it in decimal, okay? We need it to do conversions. Okay, so how does this go again? Okay, so I'm going to do a couple of examples, and hopefully that'll refresh your memory and you'll see how this goes. Oh yeah, there's something else. Okay, so let's just write this. 1938 divided by 34. Yeah, grab the calculator, right? But okay, no, we won't be able to do that. Okay, now, some of you come from the French high school, some of you come from English high schools. You have learned, or primary school, whichever, where you learn division, you've learned it differently. It's the same algorithm, but you write it down differently. I went to French school. I never went to English school. So I do it the French way, and I can't do it the English way. I'll just mess up. Okay. So I'm going to write it down the French way. And if you're doing it the English way, it's exactly the same thing, but you just don't write the numbers in the same spots. Okay. So you're in theory, you know how this works. Okay. So let's do this. So I do it this way. 1938 divided by 34. If you come from the English sector, you put that thing somewhere else. I don't know where, whatever. Okay, you know how to do it. Okay. So I don't know. The English way is just the same algorithm, but you just write the numbers in different places, but it's the same thing. Okay. All right. So how does this go? I look at 34 and I want to know how many times does it go in one? Yeah, it's the layout. Exactly. Yeah, the layout is different. So 34 doesn't go into 1. So I just now look at the next one. 19, 34. Does it go into 19? It does not. So now add another one. So now I have to figure out how many times 34 goes into 193. So you sort of do it, you do it in your head, right? So 34 times 2, that's too small, times 9, that's too big, times 5, maybe. So you just try it out, right? 5 times 34, that's 20, that's 170, and that looks right. So 5 times 34 is 170. You subtract, so that's 3, 2, okay? And then you bring down your next digit, 238. So now you have to figure out how many times does 34 go into 238, which is, let's see, if I try 6, that's probably too small. 7 looks maybe reasonable. 7 times 34. 4 times 7 is 28. 3 times 7 is 21, 23. Woohoo! Yes, 238, 0, and that's it. But either way, it's annoying to do. Absolutely, yes. I agree. So 34, oops, sorry. So 1938 is divided by 34 is precisely 57. Okay. Now I have to add something which you may not have done exactly this way before, but it's really easy. When we're going to do division, we're not going to go to, we won't need to go to fractions, right? So this particular example, we were lucky because it turns out that 34 times 57 is 1938. So no fractions, we're happy. But let's say I change it and I ask 1940 divided by 34. Let's say I had to do that, okay? So of course it's going to be exactly the same procedure. So I'll just copy down. So here I get 170. I subtract, I'll get 24, right? I bring down the 0 to 40. Now this will go 7 times again. 7 times 34 is 238. I subtract, and I get a 2, okay? Now, if you were in grade school, or high school, I don't remember, but they might have you continue, right? You get a decimal point and you keep on going. We don't want to do that. All I want is for you to notice that this is the remainder of the division, which will be important. So remainder of the division is 2, okay? So I'm dividing 1940 by 34. Okay, and it doesn't go, so 34 doesn't go exactly into 1940, right? It's 1938 when you multiply by 57, and there's this 2 that's left at the end. Of course, we could keep on going with the fraction, but I just want you to see what I mean by the remainder of the division is what you get at the very end, okay, which is smaller than what you're dividing by, okay? So let's do maybe one other example, because there's that little tricky part. Let's do 1260257 divided by 37. Okay, that's 1260257 divided by 37. Okay, it looks awful, but it's not so bad. Okay, so again, I start on the left. 37 doesn't go into 1, doesn't go into 12. I'm going to see how many times it goes into 126. 3 times 4 is 12. That's too big, so it'll be 3. 3 times 37 is 111. Okay, I subtract. That's 5. That's 1. I bring down the next digit. So that's 150. 5 is too big. 4 should be okay. 4 times 37, that's 8. 148, okay. So that's 4 times 37 is 148. I subtract, I get my 2. I bring down the 2. And this is the only reason why I'm doing this example, is what's going to happen right now, okay, which is a very common mistake or place where we mess up. So how many times does 37 go into 22? It goes
0.
0 times. Yes, exactly. So I need to put that 0 in. I really need to do that, because otherwise I'm going to mess up everything. And now I bring down the next one like this. Okay. So now I'm okay. Okay, now 37 and 225, maybe 7. 7 looks too big. 6. 6 times 37. That's 222. That's 6 times, so that's 222. I get 3. Bring down the 7. I won't write it in red. And whoo-hoo, goes 1. Remainder is 0. Okay, so it could have been non-zero. Just keep that in mind. Okay, but what I wanted to illustrate, the important point that I wanted to illustrate, is this 0 at this point here. Okay, so that's important. Don't mess that up. You won't have to be you won't have to do a lot of divisions, but you'll have to. So just be careful with that. Okay, so we've got the 4 basic operations reviewed for decimals. 3 of those we'll do in other bases. This one we won't. Okay. So now we can move on to the binary number system. So what is that? That's base 2. So it's exactly the same thing as base 10, except that rather than work with 10, powers of 10, we work with powers of 2. Okay? So we write down numbers with 2 symbols only, 0 and 1, right? Which are all the values less than 2, right? So these are the binary digits, which are also called bits for binary digits, right? That's where it comes from. So these are the 2 bits. Okay, so we're going to write down numbers using only 0 and 1. So this is like different from base 10 in terms of use, in terms of, but the principle is exactly the same. I'll discuss the use in just a sec, but let's just explain how this works. So what do I need for this? For the moment, I'll need powers of 2, which are always good to know. So 2 power 0, like for 10 is the same, it's 1. 2 power 1 is 2. 2 power 2 is 4. Just multiply by 2 every time, right? 2 power 3 is 8. 2 power 4 is 16. 2 power 5 is 32. 2 power 6 is 64. And do I need more than that? No. If you want more, you can just, you keep on multiplying by 2. Okay. So let's write down a number in binary and see what it means. So it's exactly the same principle as for decimal. So here we go. Suppose that I write down 110101 in binary. It means what? So the expanded notation is, so okay, so in decimal, if you remember, this is the place of the units, or the 10 power 0, so this will be the 2 power zeros. These will be the 2 power 1s, these will be the 2 power 2s, the 2 power 3s, the 2 power 4s, and the 2 power 5s. Okay, so this is 1 times 2 power 5 plus 1 times 2 power 4 plus 0 times 2 power 3 plus 1 times 2 power 2. I'm going to run out of room. Plus 0 times 2 power 1 plus 1 times 2 power 0. Okay? So the position tells you the power of the 2, which is the base, and you have a 0 or 1 that tells you how many of these you have. Okay, so let's just keep on going to know what this number is in decimal. That's our natural system. So that's 32 plus 16 plus 0 plus 4 plus 0 plus 1, which is 48, 52, 53. Yeah, in decimal. Okay, so this, so 110101 in binary is the same as 53 in decimal. Okay, makes sense? Is that okay?
Yep.
All right. Wonderful. Okay. All right. So let's write down, before I keep on going, let's write down the first few numbers in binary. Okay. So I'm going to, so sorry about that. It's weird. The first few numbers, I'll write them in decimal and in binary. And I want you to pay attention to the pattern, which is really important. But let's start by writing them down in decimal. So of course 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so what happens in decimal, right? The next thing is 10. So you jump 1, 0, right? Because you've reached the base. Then you keep on going. I'm going to run out of room here, obviously. So I'll just go here, 13, 14, 15, 16, 17, 18, 19. Now 20, that's twice the base. So I get a 2 and a 0 and keep on going. Okay, let's write the equivalent in binary. So this is in decimal. Let's write in binary. So 0, 1. What is 2? I've reached the base. So now it's 1, 0, right? 2 power 1 plus 0. Then 3 is 2 plus 1. So that's the next guy. 4 is 2 squared. So that's my next place, right? That's 4. And 5, 6. If you're not sure what I'm doing, it's okay. I'm just going to write them down. Maybe you see a pattern. What about 8? What is going, how that, blah, blah, sorry. Try again. 8 is 2 power 3, right? So that's a power of the base. So that's the next one, 1, 0, 0, 0. And it keeps on going. 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. And 16 is 2 power 4. So I move next like that. It's going to keep on going like that. Okay? So I'm going to do a lot more examples, okay? And I'll come back to this pattern that you may have seen or not. I mean, may have seen, I mean, you might have realized what the pattern is as I'm writing it, okay? If not, it's fine, okay? I'm going to do some more examples, loads of more examples before we keep on going. We come back to that, I mean, okay? Okay, so again, the position gives you the power of 2 as you move from right to left. The powers increase, but just like in the decimal system, you could move to the right, and then you have these negative powers, right, for fractions, okay? So the positions, you have 2 power 5, 2 power 4, 2 power 3, 2 power 2, 2 power 1, 2 power 0, and then you just keep on going, 2 power negative 1, 2 power negative 2, 2 power negative 3. This will give you the fractional part, right? And this is the integer part, just like in decimal. Okay, so let's just take a look at what these negative powers of 2 are. So 2 to the negative 1, that's 1/2. In decimal, that's 0.5, right? 2 to the power negative 2, that's 1 over, that's 0.25, right? I'll write the next one here. I don't know if I need more than that, maybe 1 over 2 power 3, that's 1/8, that's 0.125, and I might need this guy here, 1/16, which is 0.0625. Now, if we were live in class, like normal, I'd tell you, of course, we won't be able to use calculators. And so you'd say, wait a minute, am I supposed to be able to remember those? No, not the bigger ones. So if you are asked a question where you have to use these negative powers of 2, you would be provided with the values, the ones that you might need, okay? Because everything would be done by hand. Okay, so let's do another example. So let's say I write 101.1101. This is in binary. Okay, so what does that stand for? Again, positional system, powers of 2. This is power 0, power 1, power 2. So this is 1 times 2 power 2 plus 0 times 2 power 1 plus 1 times 2 power 0. That's the integer part, plus 1 times 2 power negative 1 plus 1 times 2 power negative 2 plus 0 times 2 power negative 3 plus 1 times 2 power negative 4. Okay? To see what I get in decimal, okay? So this is 4 plus 1 plus 0.5, right? This is 1/2. This is 0.25. You can look up the table here if you want. And this one is 0.0625. And if you add those up, you'll get 5.8125 decimal. Okay. So 101.1101, this is binary for 5.1825. Okay. Are there any questions up to this point? Comments? Is this going okay? Everybody's gone to sleep.
No, this is fine.
All right. Okay. Now, suppose that I write something like this. Suppose that I write 11010.11011. I just write that down. Now, it looks like it's binary, but it could be decimal, right? It could be 110,101.11011, right? So how do I know? Well, so this could be binary or decimal. Okay, so how do we tell? Okay. Well, to make sure that we're talking about the same thing, the notation will be as follows. So unless from the context, it's clear that we're looking at binary or whatever, so we'd write it this way. We'd write 110.11011 with a little 2 like that, means this number is written in binary. Okay, so that's the notation. Okay, or you might not use the brackets, but it can get a little tricky if you don't do that. Okay. All right, so that's the notation. I'm going to stop very soon. I just want to start the notion of the concept of conversion from binary to decimal and decimal to binary. Okay, So what have we seen up to now? I've reviewed decimal as a positional system and the 4 basic operations. I've introduced binary as a positional system, which is exactly the exact analog of decimal, but it's base 2 rather than base 10. Before we look at the operations in binary, I want to talk about conversions, going from binary to decimal and back and forth. So there's 2 things we need to know: binary to decimal and decimal to binary. Okay. Binary to decimal, if you think about it just a few seconds, you'll say, wait, isn't that what we've just done? And yes. All right. So this one is, this is straightforward. Yeah. Right? Because what I'm doing when I'm converting from binary to decimal is just reading the number in binary and writing out what it means, right? So, but from decimal to binary is a different thing, and I don't want to do it now. I'm going to do it next time. Okay, but let's just take a look, just to review one last example from binary to decimal. Okay, so conversion. So convert 1110011.01 to decimal. Okay, so I'm given a number in binary and I want to write it down in decimal. So what do I do is you just apply the definition basically. So we've seen this already, just apply the definition. Okay, so what is that? Well, again, position indicates the power of 2. 0, 1, 2, 3, 4, 5, 6. So it starts with 2 power 6. 1 times 2 power 6 plus 1 times 2 power 5 plus 1 times 2 power 4. I'll skip the zeros now. Okay, so this is 2 power 3, 2 power 2, 2 power 1, 1 times 2 power 1, plus 1 times 2 power 0, plus, don't mess up, don't skip powers, be careful. So these are the 2 power minus 1. This is 2 power minus 2, like that. So now I just compute. So 2 power 6 is 64. 2 power 5 is 32. 2 power 4 is 16. This is 2. This is 1. And I'll write it in decimal immediately. That's 1/4, which is 0.25. So this will be 112 plus 3 plus 0.25. So I get 115.25. Hopefully, yes. Okay. So converting from binary to decimal is just basically reading off the number as we know it's what it's supposed to mean. Okay. From decimal to binary is a completely different thing, and I don't want to do it now. We've had enough. We've had an hour of this. So what I want to do, to be continued Thursday. Okay, so I'm just going to stop the recording here.